Hi everyone. In this video, we're going to look at a certain situation that can happen when the integration by parts formula actually provides you with exactly the same integral that you started with. When that happens, we're looking at what's called a cycling problem, and it can be a more useful scenario than what it probably sounds like. So let's take a look at the details. Here's an example where if you integrated by parts twice, you'd end up with the same integral you started with. My hope is that you have enough experience with integration by parts that you can see that far ahead by now, but in case you can't, let's convince ourselves by making a prediction about where integration by parts would actually take us in this situation. As a first step, you could use sin x as f and e to the x as g prime. The opposite assignment is also possible in this case, but this is my preference mainly because e to the x is so easy to anti-differentiate. So without going through all the painstaking details, what would our new integral look like if we used the parts formula? Well, f would get differentiated to give us cos x, and g prime would get anti-differentiated to give us e to the x. That's not quite the same integral we started with, but it's pretty close. So let's see what happens if we integrate by parts again. So we assign our g prime and f in a similar way to what we did before. And by differentiating f, we get sin x, ignoring the negative since it can be pulled out front anyway. And by anti-differentiating g prime, we would get e to the x. So in case you weren't able to make this prediction all in your head, hopefully we're now all in agreement that going through these steps would provide the exact same integral that we started with. And as I suggested in the introduction, an integral that behaves this way is what's called a cycling problem, because integrating by parts has caused the integral to cycle back to its original form. That being the case, you might think integrating by parts is a waste of time here, but it turns out it's actually the right thing to do. I wouldn't blame you if you don't believe me, so let's convince ourselves by looking at all the details. So starting at the beginning, let's make our assignments of f and g prime just like we did before. We know f will become f prime by taking a derivative, and we know g prime will become g by taking an antiderivative. With that, we're ready to apply our parts formula. So as always, the integral we want is equal to f times g minus the integral of f prime g. Notice the integral we've ended up with here is consistent with the predictions that we made earlier. Our prediction also told us that integrating by parts again will cause this integral to cycle. So let's try it. Assign f and g prime similarly to how we did before. Then f becomes f prime by taking a derivative, and g prime becomes g by taking an antiderivative. It's important to notice that the entirety of our integral is going to get subtracted here, so don't forget to show that using a set of brackets. Now, as always, our integral is equal to f times g minus the integral of f prime g. Since f prime contains another negative, I've turned the minus into a plus. You can pause and check that if necessary. For good measure, let's ensure this negative gets applied to both of these terms. So after distributing the negative, you will find these results. And now you can see that our prediction was accurate. The integral we've ended up with is exactly the same as the one that we started with. So we've successfully caused the integral to cycle. But why is that a good thing? Well, notice the integral on the left doesn't actually cancel with the integral on the right. So in fact, I could collect these terms together on the left side of the equation. To do that, we would just need to add this integral to both sides, and when we do that, we'll get two copies of this integral on the left side. These other terms will also still remain on the right-hand side. Now, let me just give myself a little more space to work with to form our conclusion. So these are the results we've come up with so far, and our goal here was to figure out what this integral is equal to. And do you see where this is going? At this stage, we could just divide both sides by 2 and we'll get what we want. So we can take this as the answer to the question, but don't forget to include a plus c in the final step. If you weren't convinced that cycling can be useful before, hopefully you are now. Here's another example, although it's quite a bit less obvious that this one is a cycling integral. This integral is also deceptively important, so make sure to pay close attention to this one. In order to make cycling happen, we would need to integrate by parts. So to form two factors, we can split secant cubed as secant times secant squared. With that, we would need to assign one of these factors as f and the other as g prime, but I want you to pause and think about how you should make those assignments. So which one should be f and which one should be g prime. And when you have your answer, let's continue. The best approach here is to assign secant squared as g prime, and the reason for that is because secant squared is easy to antidifferentiate. What is the antiderivative of secant squared? Well, that would be tan x. This one should be on your formula sheet, though it should also be committed to memory by now, so if you weren't sure about that one off the top of your head, just make sure to remember it for the future. That leaves secant x to be assigned as f, and with that, we can form f prime by taking the derivative. Now we use the parts formula to see that our integral is equal to f times g, as always, minus the integral of f prime g. Pause here and make sure you agree with what I just wrote. Now, the integral we've just come up with is sec times tan squared, but the integral we started with was sec times sec squared. So it's not obvious that cycling has occurred until we realize that tan squared is almost exactly the same thing as sec squared according to a familiar trig identity. So let's use this identity and express tan squared as sec squared minus 1. Pause and confirm these details as necessary. Now, in order for cycling to occur, we need to have the integral of secant cubed on the right side, and for that we need to expand now. So I'm going to also apply the integral separately to each of these terms after expanding. My first term would be sec times sec squared, which is secant cubed, giving me the integral I wanted. And the second term is sec x times 1, which is sec x. Notice though that there's also a double negative here, so we should now be adding this term rather than subtracting it. Again, you can pause and check that if you need. Now that we've caused this integral to cycle, we can use the exact same trick that we did before. Just add this integral to both sides so they can be collected together on the left. That gives us two copies of this integral on the left side. On the right side, we still have sec x tan x, and we also still have this integral of sec x. But that is an integral we know how to evaluate. It should be on your formula sheet, so just check that to get ln absolute value of sec x plus tan x. Now that we've come this far, all we need to do is divide both sides by 2 to solve for the integral that we want. I'll choose to represent that as multiplication by a half in this case, just for cleanliness. After that, don't forget to include the plus c at the end, and you're done. I mentioned this is a deceptively important example because it turns out the integral of secant cubed comes up quite a bit more often than you would think. So you should write this one down on your formula sheet and feel free to use it from this point forward. It's a bit of a messy formula, but I do have a trick to help myself remember it. You can notice this first term represents the derivative of secant, while the second term represents the antiderivative of secant. Even when you have this on a formula sheet, I do think it's still better to have it memorized since it helps save time. So hopefully you find these observations useful for helping you remember this formula. That's it for integration by parts, so I'll wrap things up here and see you next time.